In fluid mechanics, there are two main ways to describe a flowing fluid. The first is called a system. A system follows a specific amount of fluid as it moves. The second is called a control volume. A control volume is a fixed region in space through which fluid can flow. Both methods describe the same physical process, but from different perspectives. Reynolds Transport Theorem connects these two ways of analyzing fluid motion. Let's begin with the system approach. A system is a fixed amount of matter that we choose to follow over time. In this example, the highlighted section represents a specific group of fluid particles inside the pipe. As the fluid flows downstream, the system moves with it. The system may change its position, speed, or shape, especially as it passes through a changing pipe area. However, it always contains the exact same fluid particles. No matter where those particles move, they remain part of the system. A control volume uses a different perspective. Instead of following a particular group of fluid particles, we select a region in space that we want to analyze. The dashed boundary represents the control volume. Unlike the system, the control volume remains fixed. Fluid enters through one part of the boundary, moves through the region, and exits through another. The physical boundary around the control volume is called the control surface. A control volume does not have to match the shape of the equipment exactly. It is simply an imaginary boundary chosen to make the problem easier to analyze. The difference becomes clearer when we compare the system and control volume over time. At the first moment, the highlighted system is located inside the control volume. Now, allow a small amount of time to pass. The control volume stays in the same location. The system, however, moves downstream with the fluid. The two regions may initially overlap, but they do not continue moving together. The system follows the matter. The control volume observes a location. Reynolds Transport Theorem provides the relationship between these two perspectives. Following a system may sound straightforward, but it becomes difficult in real fluid systems. Imagine trying to follow the same collection of air particles through a turbine. Those particles may accelerate, rotate, mix, and separate as they move through the machine. Tracking every particle individually would make the analysis extremely complicated. A control volume simplifies the problem by keeping the boundary fixed. Engineers only need to determine what enters, what exits, and what changes inside. Because the control volume remains fixed, conservation laws can be applied to practical engineering equipment. This approach works for steady and unsteady flows, as well as simple and complex geometries. The same control volume method can be used throughout fluid mechanics. Around a nozzle, it can help determine how pressure is converted into velocity. Around a diffuser, it can help analyze how fluid slows down and recovers pressure. Around a pipe, it can be used to study flow rate and pressure loss. Around a turbine, it helps determine forces and power output. Around a heat exchanger, it can be used to track energy entering and leaving with each fluid stream. The equipment may change, but the method remains the same. Define a region, identify what crosses its boundary, and determine what changes inside. Reynolds Transport Theorem expresses this relationship mathematically. The left side represents the rate of change of a property belonging to the moving system. The right side describes the same change from the perspective of a control volume. For this video, the individual symbols are less important than the structure of the equation. The control volume description contains two main ideas. The first is the amount of the property changing inside the control volume. The second is the amount carried into or out of the control volume by the flowing fluid. In simple terms, the change experienced by the moving system equals what changes inside the fixed region, plus what crosses its boundary. Consider a simple pipe junction. Fluid enters through one pipe and leaves through two outlets. Instead of following every individual fluid particle as it moves through the junction, we simply place a control volume around it. Now, we only need to observe what enters the control volume, what leaves it, and whether anything changes inside. That single control volume gives engineers everything they need to analyze the flow without tracking millions of individual fluid particles. This simple example shows why control volumes are so useful. A complicated motion of individual particles becomes a manageable balance of what enters, what leaves, and what changes inside. Reynolds Transport Theorem is the bridge between following the fluid and observing a fixed region in space. By using a control volume, engineers can simplify complex fluid motion into a practical engineering problem that can be analyzed and solved. Thanks for watching, and I'll see you in the next one.